Wow. I'm blown away. I'm gobsmacked. First, I would like to thank the organizers for inviting me to speak at this lovely event. I had nothing to do with that. This has been a wonderful meeting. I'm going to try and not mess it up here at the end. Everyone's been showing pictures of the birthday boy. Here's the oldest baby picture I could find of CircuitQED. As Leo mentioned, and many of you know, we have a kind of tradition in the group, which has kind of fallen by the wayside with PowerPoint and everything, but like people would bring a printout and we'd date it and sign it and things like that. And so this is a printout that I think Andreas put on my door. It's a phase of a dispersive measurement versus gate charge. And he just put the two, double question marks, like he wasn't even sure. Is this really, but it's periodic and gate charge. So maybe like we're finding the Cooper pair box with this dispersive measurement. And a lot of people have also been asking me, is your birthday today? My birthday is actually the 24th. And you can notice here, this apparently occurred on the 25th. So this was Andreas bringing me a 40th birthday present. So for all the people I'm currently working with, what are you bringing me for my birthday? Bring yourselves, that'll be enough. It was an amazing time. Things went rather quickly. We had the dispersive measurement by the March meeting, like in beautiful form. We came back, and actually my recollection is Andreas really wanted to get the vacuum Rabi splitting by tuning everything into resonance. So that's too hard. Let's just write this up. I give you like 2 weeks after the March meeting to get the vacuum Rabi splitting. And so here it is. I guess this was April. Maybe we had it working already. This is already like the draft of the figure for the paper. And we mailed it off. I think the first person we showed this to is I sent it off to Jeff Kimball, who had been my instructor for applications of quantum physics back at Caltech, and I'm not sure he ever forgave me because he was the first to observe this in the atomic domain, and it was really hard. And they never quite got to as much cooperativity and all that as these things. It was my first Nature paper. We didn't get on the cover of Nature. I don't know if they still do this. They invite you to submit some candidate cover art. And apparently the mistake we made was letting Dave draft the cover art. And so you see, you can read it here. Maybe it's faint. Biology, NIH decides to spend money on physics. Chemistry gives up in the face of bio and physics. And so if anyone who was making the decision was not like a quantum physicist, we were clearly going to get hosed. But I want to say thank you. Here's the picture of sort of the CircuitQED core back in the day. And it was a wonderful time, as a privilege to work with such special people. And not only because it was early in the lab doing experiments and things, and we were still feeling our way along, but also because we were learning this language of quantum optics and how to apply it to circuits. And I remember when we posted the paper, many of the people in the field said, I think that was a great paper, but what's a Purcell effect and why is there a vacuum Rabi? And took a while for people. Now everyone knows this lingo. And I also want to say thank you to my partners in crime for the last 20 years. Steve and Michelle, what a privilege to work with two of the best scientists on the planet for all these 20 years in close collaboration. And I don't think that's something that you're supposed to expect when you go into this as a line of work. And there's been incredible progress. We've heard a lot about it in this meeting. In the 20 years, we've gone from nanoseconds to milliseconds. That's called something, I forget what. Readout fidelities have gone up. We've heard, really amazing numbers, even advancing in the presentations in this meeting. Complexity, I guess I have to add a 0, Jerry. 1,000 qubits, size. We went from like a 2x7 millimeter chip to 30 millimeters, as Andreas told us. UN told us that we've gone from 0 mass to, I think it was 16 micrograms. Maybe there's other numbers that are bigger than that. The funding, I don't know. And I was only thinking about the academic funding. Let's not even think about the private sector funding that goes into it. But of course, there's the head count. And so it's amazing to see all these people, everyone working in this space. And I just want to say thank you to the community for all the work you've done. It makes us look good. So thank you very, very much. OK, so that's the summary of the maudlin part. What I thought I'd do, instead of giving like a sort of retrospective of everything, which you heard a much better job from Steve Girvin already, I'd tell you about some of the recent stuff that we're doing. Because after 20 years, I think it's still not getting old, CircuitQED. We're still finding out all kinds of exciting new things that you can do. And one bit of progress leads to another bit of progress. And in particular, we've been continuing to bust our heads on this very difficult problem of quantum error correction. And I think we might be actually turning a corner and being able to make some real progress. But it's also kind of fun because we've gone back to basics a little bit, and we're reinventing even the way we do our bosonic qubits with this dual rail encoding. So I'm going to tell you about some of that and some of the results. And it's actually joint results because we have a collaboration between my lab and the group of Shruti and Steve on campus, as well as the company in Science Park. And there's probably lots of people in the audience here from both organizations. So we've already heard a lot about error correction. In principle, the idea is easy. Just redundantly encode your information 1 bit or 1 quantum coherence in 3 separate physical entities. And then if all you had was bit flips, you would be able to be protected to first order from those. The problem is, of course, now you have encoded your information in 3 qubits, which have all 3 of them errors of their own. And so when you think about trying to actually gain from this, the idea is you're going to be gaining exponentially, but you're losing as you put in more of these elements. So if you think about trying to reach break even, you start with just having some decay of your information according to whatever the lifetime of that is. And then even if all of the qubits are as good as your best one, you're still going to decay 3 times faster. But we're told, OK, if we can actually measure these errors and either correct them or stabilize them, remove the entropy in some way, or even just take account of them in the bookkeeping of the way we interpret the results of the algorithm, that'll be OK, provided we can measure sort of quickly enough that multiple errors don't occur. But of course, we'll still be losing no matter what we do. But the goal, of course, of these things is to really be able to get some significant quantum error correction gain. And it's harder than just losing a factor of 3 in the beginning, because, of course, qubits don't just have, most of them, a single kind of error. They have multiple kinds of errors. And so you need to have a larger code than just 3. Maybe you need to do the surface code, which is 2-dimensional, sort of roughly speaking. Shruti probably won't like this. 1 dimension for doing bit flips, 1 dimension for doing phase flips. But we're told it's OK because there's a finite threshold. There's a point here where as long as we can get the devices to be better so that the error rate is less than about 1% or so, then we can start to gain from this error correction. And indeed, the logical error probability will be suppressed as we increase the distance or the size of this code in a way which is exponential in this ratio of how well we do past the threshold. And it's great because superconducting circuits and qubits have advanced to the point where, yeah, indeed, even the 2-qubit errors can be better than 1%, but they're not a lot better than 1%. And so we're still kind of right on the cusp of this, and so things are still pretty challenging. So nonetheless, there's been all kinds of amazing demonstrations. I'm super impressed at the amount of effort that's gone in both on the industrial side, but even in some of the academic labs on scaling these things up. And people have sort of successfully demonstrated a lot of these concepts, and we're ready to go in some sense. But here at Yale, our strategy has been a little bit different. Instead of trying to scale everything up and then hopefully getting a little bit further past the threshold, we thought we would do the following. So you know the story, I suppose. To choose a hardware-efficient approach. We're going to use a qubit or something to store the information that has fewer kinds of errors and hopefully slower errors to begin with. And we're not going to basically use the hardware to do the whole thing. We're still going to need to use, of course, conventional error correction codes. But what we want to do is make distance 3, or sort of deal with the first round of error correction in some built-in way using the physics of the devices. And if we can really control the propagation of the errors and all of that, then when you concatenate these things into larger codes, you could really be way past the threshold. The basic idea is, well, okay, if we're at a sort of a percent level now, if we could somehow in hardware get just distance 3, we'd be able to kind of have a squaring here of this physical probability. And when you stick that into your higher order code, now you'd really be past the sort of thresholds for most of these things. So the question is there a way to kind of make yourself first order robust to hopefully as many of the errors as possible, so that you only fail if you have 2 errors, and you can sort of take a typical performance of 1%, which is similar for readout, for 2-qubit gates and lots of other initialization, and go to sort of numbers that would be orders of magnitude better. And we also had this really nice talk setting things up from Shruti Puri, from whom we've learned a lot about error correction, saying that not all errors are created equal. Note the punctuation in the title slide. John, you're going to keep track? You're going to count for me? There's a sort of a hierarchy of errors, and some errors are easier to correct, like the erasures. You can also benefit if your Pauli errors are biased and you have a sort of hierarchy of those things, and you really need to avoid leakage, okay? And so that's something we're going to try and take to heart here, building into the hardware. So the idea here is we want to maximize the power of the cavities in CircuitQED, which have a kind of natural noise bias. So we've been working a lot with this flipped paradigm, if you like, of CircuitQED. It's not that the transmon qubits are the fundamental primary interest, and the resonators are there for buses or to prevent spontaneous emission or to do readout, but actually we want to use the cavities themselves also as information carriers. And the reason that we kind of thought that was good is, in fact, we started on the 3D cavities to begin doing the materials investigations for IARPA in 2009. And what we thought is by making some 3D cavities, we'll get Qs of like 10 to the 11 or 12, and then that'll be the fiducial we use to measure materials and everything. We can make them be Q of 10 to the 8 and get to several milliseconds, but still, there's mysteries even in just these 3D cavities for why they're not better than they are currently. But nonetheless, they can be still better than a transmon qubit in terms of the lifetime. And importantly, they also have a large noise bias in the sense that they have very little intrinsic dephasing. It's a linear element after all. It doesn't have any Josephson junctions. It has as small a surface participation ratio as you can manage. And we can even see that in experiments where we have this full setup. So this is from the paper by Serge Rosenblum and Phil Reinhold, where they were able to sort of tune the dispersive coupling between the transmon and the cavity. And there's a point here where they turned off the interaction so that you're no longer suffering any dephasing from the transmon. You're still actually suffering a T1 perhaps. But anyway, this thing had a cavity lifetime that was not quite a millisecond, but then you see it goes really very close to 2T1 when you turn things off. So from this and from several other experiments, we're able to place a bound and only really a bound, that the intrinsic dephasing time of these 3D cavities, for instance, is at least 10 milliseconds or longer. So there's a nice leverage there, and that's one of the reasons why these bosonic codes, which allow you to correct for photon loss, should be useful, should be a way to get gain. Okay, so again, not all errors are created equal, and in particular, these erasure errors are a special kind. What an erasure error means is that maybe an error occurs in a qubit, but you have a unique signature. There's something you can measure that doesn't involve multi-qubit properties or stabilizers. You have a flag that goes off that allows you to detect exactly when and where a qubit went wrong. And of course, that means that your information you have is much larger. You can sort of prevent the propagation of errors. And it means that the thresholds, for example, can move much higher. And so this work on dual rail and erasure qubits in superconducting cavities that we're doing is very much inspired by the recent work that Shruti did with Jeff Thompson's group at Princeton, in which they looked at being able to engineer a neutral atom platform in which most of the errors could be then detected, and by that process converted from spontaneous emission or other kinds of mechanisms into something that would be classified as an erasure. And this idea of erasure conversion, I think, is one of the biggest sort of practical advances in our understanding of how you should do error correction in recent years. There's another big advantage of having something which is erasure dominated, and that's that because in a way the errors are a little bit more classical, they seem like they scale better, or to put it more technically, a surface code can, for example, correct twice as many erasures. Now, you don't have to do the surface code, by the way. There are, of course, if you had predominantly erasures, there are other codes that are small and pretty efficient that you can use to correct the erasures directly. Okay, so that's led us to kind of consider this new way of doing bosonic error correction. We're going to use a microwave cavity. We're going to add some complexity. We're now going to encode the qubit in a pair of microwave cavities or microwave modes that have, let's say, different spatial and different frequency, different spatial modes and different frequencies. And the logical encoding is that we're going to have an excitation which is either in Alice, the left cavity, or in Bob, the right cavity. And that just gives us a simple two-level system, which is your qubit space. And the reason this is important is now if the predominant error that you're having is, of course, the excitation, which could be either on the left or on the right, disappears, then you will go to this unique state 0, 0. And in the story I'm going to show you, there's multiple ways that you can then detect the fact that the photon has been lost, and you can even do that without detecting whether it was supposed to be on the left or on the right, using mid-circuit erasures. And so there's a syndrome here, which means you can have a way to detect these errors. Now, there's a proposal paper that came out, a paper about the way in which to do the gates, and then this preprint on the archive showing some of the results on the basic properties of these qubits that I'm going to describe. So the dual rail is not new to us. It's actually a very old idea. Goes back to linear optics, of course, and proposal by Chuang and Yamamoto in just a couple of years after Shor. And there's many examples of why you would want to make something differential. You have two things and you look for the difference between them. And so there was proposal for doing this dual rail with transmons from Amazon. There's also a preprint very contemporaneous from the Amazon group demonstrating a dual rail using transmons. And then there are these earlier proposals and work from Will Oliver's group as well. So it's not that it's necessarily a unique idea, but I think the idea of doing it using microwave cavities and trying to leverage this further noise structure you have of low dephasing could prove to be more advantageous. So here's the thing. We want to simplify our task of error correction. Let's have something which has a really nice structure to its error processes. And what we can do is use the physics we know of CircuitQED and these cavities to kind of predict what the major types of errors should be and what their frequency of occurrence might turn out to be. So the erasures are going to be set by the T1 time. That's the fastest error process in the cavities. So you want your dominant error process to be the best kind, to be an erasure. And so that might be on timescales of a millisecond. If you're going to do gates on sort of frequency scales given by the dispersive coupling to a transmon, for instance, or on microsecond timescales, that means you might have a sort of 10 to the minus 3 probability of an erasure per time step of the future computer. Dephasing, again, we said, OK, that's going to be tens of milliseconds, so that'll be at least an order of magnitude suppressed. Now, what's a bit flip? Because we have these two cavities at different frequencies, essentially any linear coupling just renormalizes the mode frequencies. So if you're not doing some nonlinear process, there's almost no way for a 5 gigahertz photon to move into a 6 gigahertz cavity. The only thing that it could do is relax to the ground state and maybe get heated back up. And so that process should be sort of on timescales of minutes. It would give parts per million or parts per billion per kind of characteristic time. And like heating out of even the 2 photon space or whatever leakage, which is the worst of all errors, maybe just basically effectively never happens. Or you can, I think we can have a non-destructive way of measuring for leakage here for almost all the processes. So here's the full architecture. You want to have these two cavities. You need to be able to do operations, so you need a beam splitter interaction between them. That's going to be provided by some Josephson parametric devices. And then you're going to have an ancilla transmon, which is now going to be used to like load the photons in to measure the resulting state and to give you interaction between 2 of these dual rail qubits when you need it. And the thing that we describe in this concept paper is that using all the things we've developed over the last few years, we believe that it's possible to detect all of the dominant errors in this system, the cavity loss, and when you're using the transmon, the dephasing and the relaxation of the transmon as well, and convert them into low probabilities of erasures, which makes them much easier to deal with. And that requires you to use this sort of 3-level transmon trick. OK, so how do you do single qubit gates? You want to transfer from left to right. You need a beam splitter interaction. We can do this parametrically using sort of tools taken from the amplifier wing of the CircuitQED community and applying them to the high Q cavity domain. And one of the things that's nice is now essentially your Larmor frequency is the difference in frequencies between the 2 cavities. And you go back to sort of the standard thing of using amplitude and phase of your single RF tone that you adjust, or 2 tones if you're doing 4-wave mixing. But it makes the kind of ideas of how you control these things much simpler. Now, Shruti said, I told her, or we tell her, that beam splitters are easy. I felt like I had to defend my guys. And actually, we weren't thinking of necessarily the dual rail and that we needed to have super awesome beam splitters. We did know that for all sorts of bosonic error correction things we would want to do, we would need better beam splitters. And so we launched a couple of years ago 3 or 4 separate projects looking at different ways of getting better interactions, and 2 of them worked pretty well, actually almost equally well. And so we're not sure yet which is kind of the preferred strategy. The first of these was to use this snail device pioneered in Michelle's group here at Yale, and biasing it to the right flux point where you have predominantly 3-wave mixing, because we think not necessarily that 3-wave mixing is better than 4-wave mixing a priori, but because if you reduce the number of unwanted processes, that'll help you get a cleaner interaction. And so we figured out a way to get sort of DC flux bias and RF drive into one of these 2-mode post-cavity kinds of devices with this thing that looks like the Wright Flyer. We could show sort of parametric oscillations here between the left and the right, between Alice and Bob, that look like this. And they look sort of like a Rabi oscillation, but not, because they're sort of falling down toward the ground, and that's a good thing. That's an important sign. What that means here is that we're doing fast operations, and that predominantly we're preserving the nice error structure of the cavities. So we might be adding a little bit of extra relaxation, but usually that's very small. But we're adding even less dephasing. Dephasing would take you sort of to something where the photon is in one or the 2 boxes, but you just don't know which one. But here what's happening is really the predominant thing is just that the photon's being lost, and that means we can treat it as an erasure. The second scheme is using this parity protection and sort of flux pumping a squid device, which is essentially a transmon, but pumped in a different way. Again, this is not earth-shattering, groundbreaking news for the amplifier community. It's just us learning to do it in a way that doesn't spoil the hundreds of microseconds to milliseconds lifetimes of these devices. And so again, you can get very nice swap oscillations between things. With this device, we could go even a little faster and get down to swap times of like 100 nanoseconds or beam splitter rates of a couple of megahertz. Indeed, this looks a bit like a Rabi oscillation, so we can treat it as such and say, let's just see what we can do if we change the amplitude and the phase of this beam splitter such that we do randomized benchmarking on this block sphere formed by the single excitation manifold of Alice and Bob. And what we could see is something where we could do actually thousands of gates. The raw gate infidelity here is something a little bit better than 3 nines. But again, we're falling towards the ground state here, so we actually can do a post-selection. We can measure which ones of these randomized benchmarking trials didn't suffer the photon loss and see what the fidelity is in that case. And in that case, when we just post-select on the fact that we have to have a photon in either Alice or Bob, we're throwing out about 1 in 1,300 of the operations. But it's improving the fidelity by a significant amount. Actually, the referee said, what's the big deal about a few tenths of a tenth of a percent? It's a factor of 4 improvement, so I'm sure they weren't in this room. There's a factor of 4 improvement in the overall fidelity, which again is sort of confirming that we're preserving the noise structure where photon loss is the dominant thing. Okay, so why are we excited? This is like 2 orders of magnitude almost faster than we've been able to go in other bosonic codes like the binomial code, and also about 2 orders of magnitude higher fidelity for doing single qubit operations. Okay, so now what I want to do is switch. By the way, I'm sort of indicating which lab did the experiments with the little logo in the upper right-hand corner. So now I want to switch and tell you about using some very precise measurements with these dual rails to try and confirm more about this error hierarchy and be more specific about the phase flip and bit flip rates and all that sort of stuff. So what we're going to do here is an end-of-the-line projective measurement of the dual rail qubit, and we're going to be able to build into it this erasure detection. So just as a reminder, right, so you can do pretty good readout of transmons these days You can read the ground state very well. Typically, the fidelity is limited by the fact that a readout takes some 100 nanoseconds to a microsecond, and the T1 time then gives you about 1% or so, or maybe a few tenths of a percent probability that you've actually relaxed during the course of the measurement. The real problem here is that a single error, like a T1 during the measurement, or a misassignment of which blob you have in your histogram, leads to an incorrect conclusion about the state of the qubit going in. Now, in the dual rail, there's something really nice. Basically, all you ever have to do in state preparation and measurement is deal with Fock states. You need to make n equals 1 in your cavity, and you need to measure n equals 0 or n equals 1. And the dispersive interaction with a transmon is just built for that, right? There may be dephasing back action when you do a measurement of the photon number with a transmon, but it just doesn't matter if you're doing a preparation in one of the logical states or if you're doing a measurement in one of the logical states. And so what you can do here is you can have a transmon, for instance, on both Alice and Bob, and you can make a measurement where you map whether there's 0 or 1 photons onto grounder excited state of the transmon ancilla that's attached to those cavities. And then you perform a measurement of each transmon. You can do that in parallel, and you get 2 bits of information. And those 2 bits of information are going to tell you whether you're in 0, 1, 1, 0, which logical state you're in. But they can also give you extra information, right? They will also tell you, for example, whether you get a 0, 0, and then you can throw those out. So you're getting extra information, but also importantly, you're getting something which is now first order insensitive to a single error in this process, because you have to misassign both of the cavities to the wrong photon number in order to actually get confused about the logical state. Now, maybe if you miss a photon n equals 1, call it n equals 0, you think you're in 0, 0, and there was still a photon around, that's just some extra erasure probability. As long as that's small enough, that might be OK. Here it's pretty big, but we've been intentionally trying to optimize for the best discrimination between the logical states to use this as a sort of better microscope to look at the coherence. And so here are some of the results that are in this preprint. There's sort of preparing the 0 and 1. And by the way, the preparation can be done redundantly because you can prepare n equals 1 and then use the transmon to check and only go forward when both cavities have been correctly assigned to 0 or 1, whatever you wanted them to be. We have a model that takes into account all the coherences of the system and seems to do a pretty good job of predicting things. And so when you try to prepare, let's say, one or the other of the 2 logical states, there's some probability that you either actually or falsely get think that you've had an erasure. But if you're in the code space, it seems like you're getting it correct at the couple of parts in 10 to the 4. So you only misassign your logical state sort of 10 or 20 times out of 100,000. And that's quite a lot better than the typical readouts that one can do. OK, so as I said, now this means that we can separate out the different error mechanisms within this dual rail, and we can try and look at whether it's going to actually fulfill these predictions about the hierarchy of the error rates and the future performance you might get. So here, let's create a superposition. We do that by loading a photon into one cavity, doing a pi/2 50-50 beam splitter pulse parametrically, and then delaying for some amount of time for particular reasons. We're doing an echo in the middle, and then doing a pi/2 at the end after that. And then at the end, you do this projective measurement into the logical basis and throw away all the things that are erased. The purple here shows you the probability that you've been erased. That's just growing at a time scale of a few hundred microseconds, which corresponds to the T1 lifetime of the 3D cavities that are used here. And what you can see here is Ramsey fringes or echo fringes, and they persist out past sort of the characteristic time scale associated with the erasures, because these are keeping only the shots that are still in the logical code space. And so this is Ramsey, this is Echo, and the timescales here are pretty long. What I also find amazing about this is, like, if we just zoom in here on the short time, meaning the first 20 microseconds of this dual rail qubit, there's no adjustment here in the contrast. There's this is taking the raw shots. What you can see here is that you have resolution that allows you to say, okay, we're only getting a few parts in 10 to the 3 decrease of our Ramsey contrast or our echo contrast after 10 microseconds. So the probability of a phase flip happening is something like 2 times 10 to the minus 4 in a microsecond, which is kind of the time scale we're going to be interested in for doing gates and the like. And so that places, again, a bound on the dephasing that says we're at least bigger than a couple of milliseconds in this case. I think we still haven't seen the bottom here. So there can be other exogenous effects that look like dephasing. And there's also potentially issues with just, even though the measurement's very good, deconvolving the measurement precisely is a good question. Okay. Now, I said that even after you've gotten rid of the erasures, there's supposed to be a strong hierarchy between bit flips and phase flips, which again can be advantageous, at least if you're just having the qubits idling and sitting around. So we can look at sort of the bit flip rate by either preparing one of the 2 logical states and then as a function of time, looking to see the probability that you stay in the, you think you stayed in the initial logical state. This is actually polluted here by the fact that as the erasures become of order 1, or start rising here, it's just getting up to, sorry, it's over here. Yeah, erasure is getting up to about of order 1. Now, any small probability that you take the erased state and assign it to be the wrong logical state can kind of dominate. But again, you see that these curves are quite flat. We can place a bound here that the bit flip lifetime is something like 50 to 100 milliseconds. I mentioned that the bit flip should be dominated by relaxation and then heating. In a separate experiment, we can measure the heating rate. The excited state thermal equilibrium population of these cavities is about 10 to the minus 3 or 10 to the minus 4. So the actual bit flip lifetime we would predict is something like 15 minutes. Okay, enough that it just doesn't matter, right? At least when you're idling. Okay, so then let me, guess they didn't give me a strict time limit, so I'm going to take a privilege and go slowly and finish off with a few things here. So I mentioned that you want to not only be able to do a detection of the photon loss at the end, but you also want to be able to check for erasures during an operation, and you want to do that in a way that's not also going to perturb the logical state. So if we wanted to measure a change in photon number or a photon loss in one of the usual bosonic codes, what we would do is monitor the cavity parity. Here, to detect whether there's a photon lost from either Alice or Bob, what we need to do is measure the joint photon number parity, or we want to know whether the system is in 0, 0. And so there's a way to do that even if you only have a transmon attached to one of the 2 cavities. And the reason for that is when we drive a beam splitter, what we're doing is swapping the photon back and forth. So if you like, the transmon is sensing both the photons that started in Alice and the photons that started in Bob. Or it's effectively making these 2 distinct modes look indistinguishable. Okay? And so I'll show you some very recent results from Stein de Graaf and Sophia Xu, who's in the audience. Stein, I think, is out with something. But what I'm going to show you here is joint photon number splitting. So what they do is basically we just can look at the spectrum of the transmon here as a function of frequency and the sort of probability that you get excited. And so just do spectroscopy of the transmon, while you change the beam splitter rate. And to start with, if we just are in the vacuum, there's just one peak. This is not surprising. But if you start with one photon in the system somewhere, and you begin driving the beam splitter, what you see is that here there are sort of two peaks that are offset. And as you drive the beam splitter harder and harder, the states kind of evolve. As I said, you're making things kind of go from originally left and right, and you're turning these on, you're getting these sort of symmetric and anti-symmetric combinations. And so now the plus and the minus state, or what was left and right, are no longer distinguishable. It's probably not the best. This is the first time I'm explaining this, so it's probably not the best way. But what you can also see here in the spectrum is this faint line. That comes from the residual 0-0 population. That's the peak at which the transmon would be excited if you had no photons in the system. And so to do a check for erasures on the fly, what you do is just a spectroscopic pulse about that frequency, which takes a time of order chi, or chi over 2 actually, because you're only sensing the photons half the time. And so we'll drive with a beam splitter here, which is on the order of chi, the dispersive coupling, and look at what results. And so here is sort of performing pairs of these erasure checks. If we start with superposition, you can see the following kinds of things. So there's some probability that per check you have an erasure actually occurring. That's the green line. There's some increased probability of falsely declaring an erasure, so that's something like 4% per check. But then if you look at the decay of the z-logical information, it's pretty slow. In fact, it actually seems to improve the contrast of the Ramsey. So we can infer from that that there's sort of a few tenths % probability of inducing a phase flip per one of these erasure checks. And you can also do the same thing to look at the bit flip rate per check. This doesn't come because of heating or something like that, but because you're swapping many times and you need to make sure you've done the swaps precisely enough. So a little bit the phase of the beam splitter or the precision of the beam splitter turns into something that looks like bit flips. Okay, so this kind of thing is the primitive that you need for doing 2-qubit gates. And so again, in these concept papers, we describe a way of doing the gates. What you need to do if you want to do an entangling operation between two of these dual rails is engineer some kind of an interaction between them. And so if the two individual dual rails here share a beam splitter, and you drive that beam splitter, you can effectively measure the joint parity of these two, which will depend on not whether you're erased, but on which logical states the two qubits were in. And you can make this kind of exponentiation gadget where the transmon will end up in the ground state at the end, provided you did everything right, and you impart a ZZ phase on this pair of qubits. And of course, the transmon now is being used to give you the nonlinearities to sort of engineer this Kerr. The downside is you're suffering from transmon decoherence. But with the 3-level transmon, by detecting the transmon at the end, both relaxation and dephasing can be found and turned into erasures. And so we get a sort of a flag, just like you would want, not only of when a qubit's been erased, but when a gate goes wrong. And we can classify that as well as an erasure, although it'd be an erasure now on a pair of qubits. So if one just puts in kind of typical coherence times and typical dispersive couplings, that means this gate will take on the order of a microsecond or two. And the erasure errors should be on the % level. That's kind of like the standard problem everyone has. But the residual Pauli errors come from sort of second order things or the intrinsic dephasing rate of the cavity. And we think those might even be on the order of 10 to the minus 4. And so now you don't want to talk about the fidelity. You have to talk about multiple kinds of fidelities. What's the probability of this erasure error occurring, which is easier to deal with than the probability of a Pauli error occurring. And again, these erasure errors, they can be corrected more rapidly, and they have a higher threshold. And so together with Shruti's team, we've done some simulations for this system. By the way, that means that if you have, maybe I should go back for 1 sec. Having a factor of 100 between these is kind of nice because it means that essentially you're gaining, even with your sort of factor of 5 or 10 past the erasure threshold, something like beating the traditional surface code threshold by a factor of 100. So you'd sort of like to have these things spaced out in this nice way. So if we do some simulations with kind of typical coherence properties, and you can get erasure rates on the order of 1% or maybe a little bit less than 1%, and you really can get Pauli errors on the order of 10 to the minus 4. Even though you're post-selecting on all the gates that went wrong, the surface code can correct for that and give you something which in principle should have an error correction gain of something like 1 to 2 orders of magnitude per layer. So that feels like something that's actually worth building into a code and scaling up. So the sort of lesson here, if you didn't take away any of the details, is that there's a cheat. Error detection is kind of a way to bootstrap yourself potentially towards full error correction. So that's, I think, quite amazing and something I learned again from Shruti and Jeff. So can you make this thing into a surface code? Yes, you could. It's not a small part count, so that might not be an RSL job, but you only need actually coordination 3 between your individual cavities to give you sort of a 2D grid of these dual rails. And you also don't need a transmon on every site. As Shruti was saying, you can sprinkle them around. You might only even need transmons on your measure qubits in the surface code, for instance. And again, you can also use other smaller codes. 3D cavities are not the only thing. Inspired by the kind of work you just heard about from Natalie, and working together with Natalie and Andrew's team, we have replicated this tantalum process. And in this preprint from my student Suhas, we demonstrated that we could sort of have a budget that predicts why a hybrid transmon is about 300 microseconds, but also why a on-chip resonator made of tantalum should always beat the Josephson junction. Basically, you can have a lower surface participation ratio. So you don't have to think of linear resonators as only the 3D things. No matter what materials you have, what form factor you make, you should always be able to make a longer T1 and a much longer T5 for a linear resonator. So that's maybe the reason why you might want to do these things. And so the fact that these are always longer and that this now becomes a little bit more modular and easier to scale sort of looks like a very nice thing as well. Okay, so thanks for indulging me. I'm not sure how long I went on. I wanted to thank the entire team, both on campus and at QCI, and thank very much Shruti and Steve. And maybe I will just leave some conclusions and summary here and take any questions. Thanks. There's a couple.
So this, of course, it's a very nice talk, and this is very exciting, this new type of error correction. In the CAD code paper of Nissim and Andre, there was a optimization that had to be done on how frequently you do the measurement and checking. How does that work here?
Yeah, so I don't know that I understand all of the details of that yet. Let me go back to the mid-circuit check. So, if you're trying to correct for these erasures in a higher level code and not just do post-selection, then you have to interrogate and perform this check. You'd like to do the check as frequently as you can, and it matters what the back action is, right? And so these sort of bit flip and phase flip probabilities per check are the kinds of things that will enter in, and there's going to be some optimal measurement strategy depending on the T1 of your cavity and so on. But in the sort of CAT code, you're basically exciting the transmon 100% the whole time. In this spectroscopic thing, you're just exciting it primarily when you've already had an erasure, and so you then don't care about the kind of back action that limited the cat code. But in addition, sort of chi T1 in that experiment was something like 20, I think. And so here, effectively, it's getting up towards a larger number, like 500, maybe. So stay tuned. That's an interesting question. I think that trade-off is universal no matter what you're doing in error correction.
So the very top of Shruti's pyramid was biased erasures. And I guess you don't have any biased erasures here because your encoding is 0, 1, and 1, 0. Is there anything, like, are you just so far out that it doesn't matter, or is there anything to gain from trying to come up with a new coding scheme where you can have biased erasures?
Right. So indeed, biased erasures can buy you another, factor of 2 or so in the threshold. I don't know of a way to have biased erasures for just the cavity photon loss. I do think it may be possible to get biased erasures for the gate errors.
Well,
Basically, you can figure out where the qubits were based on what you see after the transmon has caused a problem.
Well, if you had a logical space that was, I don't know, 2, 0, and 1, 1, or something silly, wouldn't that be a biased erasure? Because then you would decay out of the 2 state faster.
Yes, but what you want is something where, but maybe you're just making, you want biased erasures, but you don't want to get biased erasures by making one of the rates faster. You want to make one of the rates
Something
go to
to be
0,
slower,
right? So that's another aspect in which I think the dual rail is kind of one of these happy surprises. You only need 1 photon, so the overhead in terms of the how many times kappa is pretty minimal.
So this is really cool work. Post-selection is also the domain of weird physics, like anomalous weak values and non-Hermitian Hamiltonians. And do you get weird effects from those things, and or can you use like weak value amplification to make errors
I
bigger,
haven't
improve
thought
measurements?
about the weak value amplification. There is one bug that a dual rail has that's sort of non-Hermitian. So if your cavity lifetimes are not equivalent, then if you wait around long enough, you will almost certainly be in whichever of the 2 cavities had the slightly longer lifetime. It turns out that kind of evolution, though, is sort of deterministic. So if you just make sure that you have an echo pulse midway between when you're using things, then you spend just as much time in each of the logical states with the excitation in each of the physical cavities. And in fact, we see that can sort of undo this no-jump back action that you get. And there's other reasons why it's nice to have echoes in everybody's things, so I think that's not much of a penalty.
Cool.
But if you have other ideas about what to do, you should talk.
Okay, if we don't have any more questions, let's thank Rob again.
Okay. I think it's going to be then up to me to close the conference. So before you guys get up, I'd love to thank all of the speakers. This has been an amazing meeting. Thank you all for coming.